So let's compare this idea of energy density to what we saw about energy in 7a. Because I think the comparison to the previous stuff is going to be very useful here. In 7a, we were talking about conservation of energy, which means let's say in a closed system, what would we generally assume about energy in a closed system? What do we mean about conservation of it, or what do we mean by conservation of energy there? What should we expect about the total energy? That there's no energy at all? Yeah.
It doesn't like, oh, never mind.
Sorry, go ahead.
I was just going to say it doesn't change. That's what
right. We should assume the total energy doesn't change if it's a closed system. So we got to be careful about the terminology there. We don't want to say that the total energy is zero. We want to say the change in total energy is zero. That is, that the total energy is some presumably non-zero value, but it's a constant value. Its change is zero, no change at all. Or alternatively, if it's an open system, what should we expect delta E total to equal? What could be causing that change in total energy? Right, heat or work, or possibly a combination of both. So in a closed system, we expect the change in total energy to be zero. In an open system, we expect the change in total energy to be heat plus work. The processes that are happening to make that change occur. And that delta, how do you typically calculate delta in these cases? How would you usually write out any delta something? Yeah, final minus initial. And the initial and final there are implied to be some initial earlier time and some final later time. So all these deltas are from some earlier initial instant in time to some final instant in time. We're talking about changes as time passes, caused by heat and work happening during that period of time. And in 7b, with all this fluid flow stuff, we're going to be looking at a similar concept, but we're going to make some subtle changes. Conservation of energy density. So the two main differences, first of all, instead of looking at the total energy of the system, we're looking at how concentrated the energy is. Energy density means energy over volume. In the same sense that, for instance, mass density is mass over volume. So formally, we might call this mass density or just density, and that's just mass over volume. It's not talking about how massive the object is, it's talking about how concentrated the mass is. So for instance, iron would be very high density because it's got a lot of mass per unit of volume. Styrofoam would be very low density because it's got very little mass per unit of volume. And we usually call that the Greek letter rho. Yeah, the Greek letter rho, which looks kind of like a curvy lowercase p, is the symbol we usually use for density in terms of how massive it is per unit of volume. Energy density doesn't really have its own symbol. It's just written as E over V or E over volume. Sometimes we write out volume to avoid confusing it with other values like voltage. But if you see a capital V, that means volume. So we're talking about not the total energy, but just how concentrated the energy is. And then the change in energy density, delta E over volume, would be how much the energy density is changing. Not from time to time, because we're assuming this is a steady state system. We're assuming this does not change significantly as time passes. Instead, all the deltas we're going to be looking at here are comparing a location and another location. So it's describing a change or a difference from location 1 to location 2. So describing how things are different from comparing a location in the fluid to another location in the same fluid, rather than from an instant in time to another instant in time. So that's what all the deltas we're talking about here. Differences from location to location rather than from time to time. And we can still write out the idea of conservation of energy density. Conservation of energy density, we would say the change in E total per volume. We could still have heat and work, but we'd be talking about heat density and work density. Work per unit of volume and heat per unit of volume. So instead of talking about from time to time how much work is transferred and how much heat is transferred, we're talking about within this fluid from location to location, how much work per cubic meter is gained or lost and how much heat per cubic meter is gained or lost. Any questions on the meaning of that density so far? And in a typical situation here, let's say we've got some pipes. Something like this maybe. And we've got fluid flowing through these pipes. So the pipe's full of water or some other fluid, and maybe it's moving around. As the fluid flows, if we're comparing location to location, and again, we're assuming nothing is changing significantly as time passes, but if we want to compare, let's say, this location and this location, what kinds of energy might be changing from location to location? If we want to compare energy of the fluid at this location and energy of the fluid at this location. Yeah, there might be some potential energy of gravity involved. These locations are at different heights, so we should expect some potential energy of gravity. So expanding the delta E total, we've got a change in potential energy of gravity per unit of volume. And what else might be changing about the fluid from location to location in terms of types of energy? What are some other energies we saw in 7A that might be relevant here? Yeah, they might be traveling at different speeds. Maybe you've got fluid traveling fast at one location and slower at another location. So you could have a change in kinetic energy density. Again, we don't really care about the total amount of kinetic energy. We just care how concentrated it is. Change in kinetic energy per cubic meter or per liter or per whatever unit of measurement you're using. So we've got a change in potential energy density if the two locations we're comparing are different heights. And note that all that matters there is the initial and final, 0.1 and 0.2. Since we're talking about a change, we don't really care what happens in between. We just care about, are the two locations at the same height or at different heights? Are the two locations involving fluid flowing at the same speed or different speeds? So that's all that matters. The initial and final values, or location 1 and location 2, is all that matters for delta whatever. And if we fill in the formulas there, what's the usual formula for change in potential energy of gravity that we used in 7A? Yeah, if we write potential energy of gravity as mg delta y, and likewise, what's our usual formula for change in kinetic energy from 7A? Right, half the mass times the change in squared speed. And I'll put the squared speed in parentheses because it's the change in squared speed. Final speed squared minus initial speed squared. However, both of these have a simplification we can do. Both of these involve a mass divided by a volume. And what do we call mass divided by volume? Yeah, mass divided by volume is the density, rho, the density of the material itself. So mass over volume can be replaced with just density of the material, rho, in both of these. So for both of these, we can just write this as density times gravity times delta y plus density over 2 times delta speed squared. So we now have some much more straightforward, much simpler formulas for these changes in energy density. And that density is just the density of the fluid. So if this is water, you'd use density of water times acceleration of gravity on Earth, or whatever planet this is taking place on, times the difference in altitude between these two locations. And that's just the absolute difference. Like you might say one of them is 3 meters higher than the other, or something like that. It doesn't really matter how much more water is above or below. All that matters is comparing these two locations. What's the difference in altitude, the difference in elevation? And then for kinetic energy density, half the density times the difference in squared speed. That is speed of the fluid here squared minus speed of the fluid here squared. And it doesn't really matter which order you subtract in as long as you're consistent about it. Because we're not talking about time here. There's no final and initial. There's just location 1 and location 2. So the order you subtract in for the deltas doesn't really matter as long as you're consistent about it. However, if you happen to know which direction the fluid is flowing, it's often easier to understand what's going on if you think of it in terms of the final location where the water will be minus the initial location where the water will be. Again, doesn't really matter which order you subtract, but subtracting in the order the fluid is flowing often makes it easier to understand. Any questions on those formulas so far? And meanwhile, on the other side of the equation, we've got work done per unit of volume, that is work density, and heat flow per unit of volume, heat density. Conceptually, what do you think could be doing work to the fluid? Like what could be pushing on the fluid as it flows within the pipe? Yeah, maybe there's a pump. So this could be work done by the pump per unit of volume. In the sense that as fluid flows through a pump, the pump is pushing on the fluid as it flows, and the pump does a certain amount of work, a certain number of joules of work to every cubic meter of fluid that flows past it. So that ratio is constant. It'll be some constant amount of joules per cubic meter of work done by the pump. So for instance, if a pump has a rating of 50 joules per cubic meter, that means every cubic meter of water that flows through the pump gets 50 joules of energy added to it by the push of the pump. But that's really all the pump does. The pump provides a boost in energy density that is a constant amount. And that's often abbreviated as just E or an epsilon. It is an energy density or a work density, but it's often abbreviated as just E pump. And that should be a constant. If there's a pump in the system, then E pump is going to be constant. If there's not, then it's going to be 0. What about heat? Is there any way the fluid could be gaining or losing heat as it flows? Or anything else that could be pushing on the fluid or dragging on the fluid as it flows? Yeah, you could have resistance, that is from the walls of the pipe itself. As the fluid flows, let's say you've got fluid flowing through a pipe, the portion of the fluid near the walls is dragging on the walls, and that makes it difficult to flow. Fluid in the middle of the pipe is flowing fairly easily. So if you've got a very wide pipe, the fluid is mostly in the interior and flows easily. But for a narrow pipe, most of the fluid is adjacent to the walls, and that makes it more difficult to flow. So that causes friction and energy density loss. That is, as the fluid flows, the points further downstream will have lost energy density as compared to the points further upstream. Because as the fluid flows, it's losing energy density due to friction with the walls. And so we have, since it's a loss in energy density, we usually refer to this as minus. And what aspects of the fluid flow do you think are going to determine how much energy it loses due to that friction, that contact with the walls? Yeah, how fast it's flowing. And we describe how fast it's flowing as current. So let me go off to the side here. Let's define current. Current, also known as the volumetric flow rate, is just a measure of how fast the fluid is flowing. But we got to be careful about what we mean by how fast, because we're not talking about speed. We're not talking about distance traveled per second. This is a volumetric flow rate. So it's still defined as a rate of change as time passes. But change in what? How would you describe how much fluid has flowed? Yeah, and this is really why it's called volumetric flow rate in the first place. It's the change in volume over change in time. So we would describe the current as maybe like 5 cubic meters per second. We're describing how much fluid, measured as a volume, flows past this point per second. So cubic meters per second or liters per hour or whatever unit of volume divided by whatever unit of time. Usually we're going to be using cubic meters per second because that matches nicely with the other units of measurement we usually use, the SI units. But this is how we define current. This is what current means. And we can use similar definitions for other types of current. Like when we get to electrical flow, we're going to be defining electrical current as charge over time, how much charge flows through the wire per second. In general, current is going to be defined as change in whatever is flowing divided by change in time. In this context, we're measuring the fluid flow in terms of volume per unit of time. So that's the definition of current. And if the current's flowing very fast, it's going to be dragging against the walls much more strongly. It's going to be more difficult or more pushback from the walls. Whereas if it's flowing very slowly, it's hardly brushing against the walls at all. So it's going to be easier to flow. But generally, the faster current is flowing, the more pushback you're going to get from the walls. So we should expect the heat loss, the Q over volume, the heat density loss, to be proportional to current. Specifically, current times something. Because the whole idea of proportionality is that it's equal to the other variable times some constant. And what do we call that constant? What do we call that multiplier that turns current into energy density loss due to friction? Yeah, we call this the resistance. So negative current times resistance, this is describing the loss in energy density due to contact with the walls of the pipe. And current is just talking about the faster current is flowing, the more energy density you lose as you flow through that pipe. R itself is a constant that's more a property of the pipe itself. It involves things like the length of the pipe. A longer pipe will have longer resistance. The cross-sectional area of the pipe, a wider pipe has less resistance because it's easier to flow through. And also the material of the fluid itself. I think mostly the viscosity. A more viscous fluid like syrup or something will lead to larger resistance values. Thinner, less viscous fluid like water or alcohol is easier to flow. So it's going to have a lower value of resistance or lower viscosity leading to lower resistances. But resistance is all about a section of pipe. Like we might say this section of pipe with a certain fluid flowing through it has a certain value of resistance. This section of pipe has another different value of resistance. And this section of pipe has another value of resistance. But if the pipes are in series, like one after the other, you can just add the resistances together. Resistance of this section plus resistance of this section plus resistance of this section plus resistance of this section becomes resistance of the entire pipe. So resistances are additive if the pipes are in series with each other, one after the other. And resistance in general should be proportional to length. Everything else being equal, a pipe that is twice as long will have twice as much resistance. Any other questions on those terms so far? And there's one other thing we're going to need, and I think it might make this a little more clear if we look at a very simplified example. Like, let's say instead of having fluid flowing, let's say we've just got a container of fluid with no flow at all. Like, let's say a swimming pool. We've got a swimming pool full of water. And let's say we're just comparing a location at the top and a location at the bottom. If you compare a location at the top and a location at the bottom, is there a change in height? Yeah, we definitely want to include the rho g delta y term because there is definitely a difference in height here. One of the points is at a higher elevation, one of the points is at a lower elevation. Is there any difference in squared speed between these two locations? No. Presumably the fluid in this container, the water in this swimming pool, is not moving at all. So since the fluid is not moving, we have 0 as the speed at one point, 0 as the speed at the other point. There's no change. They're both at the same 0 speed. Is there any pump between those two locations? No pump, so we can ignore this term entirely. What about current times resistance? Should we include that term? Right, because even if the walls of the swimming pool do technically have resistance, the fluid's not flowing. There's no motion. If the fluid's not flowing, then I is 0, so this whole term becomes 0. But we run into a slight problem here. There's definitely a difference in height, so rho g delta y is non-zero, but all the other terms are 0. That means we're going to need one more term in this equation. And conceptually, what else would you expect to be changing? If you start at the top of a swimming pool and you dive down to the bottom, you're losing potential energy density. What else would you notice is changing as you dive down to the bottom of the pool? Yeah, you get an increase in pressure. At the bottom of the pool, you're going to feel the fluid pushing in on you, most notably in your inner ear, because that's the most sensitive part to pressure. You're going to feel this push inwards. And that pressure also technically counts as an energy density. Even though it doesn't really look like the form of energy over volume, pressure is defined as force over area. Pressure equals force divided by area. That is the amount of force of the water pushing in on you divided by the surface area of your body. Or at the bottom of the pool, the total force of the water pushing down on the floor divided by the area of the floor. Or even on a patch of wall, the water is pushing outwards on the wall. You could take the force on the wall divided by the cross-sectional area of the wall itself. And at any given location, the pressure should be a constant value. It changes from location to location, especially from elevation to elevation. But pressure is just some value associated with the water at each location. And if you take force divided by area, that ends up having the same units of measurement as energy divided by volume. In fact, if we take a quick look at the units there, what are the usual units for force? Yeah, force is typically measured in newtons. And what would you measure area in terms of units? Yeah, meters squared or some distance squared. Yeah, because typically for calculating an area, you're going to be multiplying a distance times a distance. Simplest example, a rectangle, you just got length times width. So a distance times a distance would be distance squared, or in terms of units, meters squared. So pressure is going to be measured in newtons per meter squared, which is also described as pascals, abbreviated as PA. So 1 Pascal of pressure means 1 Newton per square meter. And this is actually a remarkably small quantity of pressure. The usual example I've got is if you take an object whose weight is 1 Newton, like a typical, let's say an apple. You take 1 apple, chop it up to make applesauce, and spread it out over 1 square meter of tabletop, which is pretty big. The weight of that applesauce pushing down on the whole table averages out to about 1 Pascal of pressure on the table. So 1 Pascal is a very small amount of pressure. In fact, just the pressure we're getting from the air pushing on us all the time is about 100,000 pascals. So 1 Pascal is only about 1/100,000th of the atmospheric pressure we're dealing with on an everyday basis. And so we usually describe things in kilopascals because 1 Pascal is so small. However, if you take this fraction, newtons over square meters, and multiply the top and bottom, numerator and denominator, by meters, newtons times meters is joules. Meters squared times meters is meters cubed. So pascals, defined as newtons per square meters, is also the same as joules per cubic meter, which suggests energy density. Joules is energy, cubic meters is volume. So energy density can also be described in pascals. And so because even though pressure doesn't really look like an energy density, it's defined as force over area instead of energy over volume, it has the same units, which means we can add it to other energy densities and it all fits together. So we really just need one more term here. In the Bernoulli equation, this whole equation with energy density, we've also got delta pressure. And this whole thing altogether is the complete Bernoulli equation. If you take all these terms together, actually copy it. This whole thing. We've got a delta pressure because the 2 points could be at different pressure. Potential energy density difference, rho g delta y, because the 2 points could be at different location, different heights. Possibly a kinetic energy density if the 2 points have different speeds of fluid. A work density done by the pump, and density loss, energy density loss due to current flowing through pipe with resistance. This whole thing, all these terms together, is called the Bernoulli equation. And that's taking into account all the possible differences between the locations. In most cases, we don't need all of those. For instance, in this example, comparing these two locations, the only differences are pressure and height. So our simplified Bernoulli equation, incorporating just the terms that are actually changing here, would just be delta pressure plus rho g delta height equals 0, since there's no other terms that are playing a role here. And this simplified equation, we usually call the hydrostatic Bernoulli equation. Hydrostatic just meaning the fluid is not moving. So anytime the fluid is not moving, and of course no pump, then you can use this simplified version of the Bernoulli equation. In which case, these 2 points are at different heights, and therefore they're at different pressures. And we could even solve this for delta pressure. Just subtract rho g delta y from both sides. And we get that the change in pressure from one point to the other is negative. That is the opposite of density of the fluid times acceleration of gravity on the planet times change in height. And again, the order you subtract doesn't matter as long as you're consistent about it. So choose at the beginning top minus bottom or bottom minus top and stick to it the whole time. Any questions on that so far? Also, just to bring some actual numbers into this, what's the density of water specifically? Yeah, 1 gram per milliliter. Can we convert that to kilograms and cubic meters? Yeah, if you run some unit conversion wizardry, grams to kilograms involves a times 1,000 or divided by 1,000. Milliliters to cubic meters involves times a million. So we end up with overall times 1,000. And the numbers work out really nicely here because the metric system is in large part defined in terms of water to begin with. 1 gram was originally defined as the mass of exactly 1 milliliter of water. That is, if you take a cube 1 centimeter along each side and fill it with water, that's exactly 1 gram of water by the original definition. And if you take 1,000 of those, or 1,000 kilograms in a cubic meter, that's the density of water. That is, if you take a box 1 meter along each side, 1 meter cubed, and fill it with water, that's 1,000 kilograms of water. Water is pretty heavy. And also that's a heck of a lot of water. So that's the standard density of water. And that's worth memorizing because it's a nice big round number, easy to remember. And water is going to show up all the time in pretty much almost all of the examples we work with. So if we fill that in, specifically for water, density of water is 1,000. And what's gravity on Earth? What's the acceleration of gravity? Yeah, or pretty close to 10. More realistically, it's about 9.8 meters per second squared, but let's round it off to about 10. So density, 1,000 kilograms per cubic meter times 10 meters per second squared times delta y. So that's the change in pressure. 1,000 kilograms per cubic meter times 10 meters per second squared times delta y. That is how much the height changes. And if we combine the 1,000 and the 10, we get 10,000. And these units are all going to work out to pascals, assuming that delta y is measured in meters. So 1 meter of height change, if you go down 1 meter in water, that's a negative value for delta y, so you get a positive value for delta p. If you go down 1 meter in water, you gain 10,000 pascals of pressure. And again, like I said, 1 pascal is very small. Going down 1 meter underwater means you're gaining an extra 10,000 pascals of pressure. So if you go down 1 meter, you get an extra plus 10,000 pascals. Go down 3 meters, you get an extra plus 30,000 pascals. And some nice standardized units, or standardized values we might want to use there. What's a convenient common amount of pressure to be dealing with instead of just a pascal? Yeah, atmospheres. The usual standard reference value for pressure other than a pascal is atmospheres. It's about, I think it's 101.3 thousand pascals or kilopascals. But for our purposes, we can round that off to about 100,000 pascals. So, and we usually call this 1 atmosphere, 1 ATM. So 1 atmosphere, 1 ATM is about 100,000 pascals, more realistically 101,300 pascals. But 100,000, if we round it off, becomes a nice neat multiple of this 1,000 times 10. So if we go back to the 1,000 kilograms per cubic meter for water times 10 meters per second squared for Earth's gravity approximately, how much height difference would you need to get an extra 1 atmosphere of pressure? If you want delta pressure to be 1 atmosphere, 100,000 pascals, how much delta y would you need to achieve that? Yeah, 10,000 times 10 meters would become 100,000 pascals. So when diving in water, every extra 10 meters of depth causes an extra 1 atmosphere of more pressure. And note that that's an extra 1 atmosphere of more pressure above and beyond whatever pressure you already had. For example, if you're at the top of the water, how much pressure are you already experiencing? Yeah, we've got 1 atmosphere of the air above you, just the column of air above you all the way up to space. That much air pressing down on you is a standard 1 atmosphere of pressure already. If you dive an extra 10 meters down below the surface, you get 1 atmosphere more for a total of 2 atmospheres. And then beyond that, every extra 10 meters you dive gives you an extra plus 1 more atmosphere. Keep in mind, these are all talking about delta pressure. So the change in pressure from diving down 10 more meters is an extra 1 more atmosphere of pressure, an extra 100,000 pascals. So that's a good standard reference point that's often useful. Every extra 10 meters of depth in water is about an extra 1 atmosphere of pressure. Or alternatively, if we look on the smaller scale, what about if we're going, let's say, just 1 meter is kind of far underwater in terms of the experiments we're typically going to be doing. We might want to work with smaller scale, maybe centimeters. Every 1 centimeter of depth in water. If you're just going 1 centimeter, what fraction of a meter is that? Yeah, 1/100th. So we take this 1,000 times 10 from earlier and multiply by 1/100th, and what do we get? What would be 1,000 times 10 times 1/100th of a meter? Yeah, you just get, wait, is that 10? 1,000 times 1/100th would be 10, but we've got an extra times 10 beyond that as well. So that should be 100. So every 1 centimeter of depth in water corresponds to an extra plus 100 pascals of pressure. Which means if you've got a column of water that's, let's say, 5 centimeters tall, the bottom will be 500 pascals more pressure than the top. And this is a very convenient standard of measurement as well. It is rounded off a little bit because gravity is actually 9.8 rather than 10. But you can use a centimeter as a de facto pressure gauge if you're talking about water. If you've got some container of water and you just put a ruler on the side marked in centimeters, instead of reading it as 1 centimeter, 2 centimeters, 3 centimeters, you could read it as 100 pascals, 200 pascals, 300 pascals of extra pressure. Every 1 centimeter you go down in water corresponds to an extra 100 pascals of pressure. So that's a very convenient reference measurement as well. Any other questions on that so far? And generally, when you're writing out the Bernoulli equation, you typically don't need all 5 of these terms. In most cases, I would expect only 2 or 3 of them to actually be changing from location to location. So it's an important skill to be able to decide which ones you actually need to consider. Like pressure, for instance, you would almost always want to include delta pressure because pressure is often something that changes to make up for other changes. Generally, I would only leave out delta pressure if you have some reason to know that 2 locations are at the same pressure. For instance, maybe you've got a location that's exposed to the open air and another location that's also exposed to the open air. In that case, both of those points would be at 1 atmosphere of pressure, so there's no difference in pressure. But more generally, unless you have reason to believe that they're at the same pressure guaranteed, unless you know that, I would recommend filling in delta pressure as an unknown, because that's usually what changes to make up for other changes. As for rho g delta y, are there any circumstances when you could ignore that term entirely and just leave that out? When would you be able to just leave that term out of the equation? Yeah, if the 2 locations are at the same level, if they're exactly the same altitude or elevation as each other. And note that it doesn't matter what happens in between. You might have some weird curvy pipe in between, but as long as the 2 locations are at the same absolute altitude as each other, regardless of what else is going on in the system, then delta y would be 0. However, that only guarantees no change in pressure if it's hydrostatic. Keep in mind that the delta y is talking about elevation. It's not talking about pressure necessarily. the pressure is really determined by all the other terms combined. So if the 2 points are at the same level, all that tells you directly is that delta y is 0. And what about speed? Are there any circumstances where you expect two locations in the same pipe to be traveling at different speeds? Like for instance, in this pipe, let's say we've got fluid flowing. Would you expect these two locations I've marked here to be the same speed or different speeds? And why would we know those have to be different? Which one would you expect to be faster and why? Yeah, smaller area is going to have a faster speed. This is the same principle as like if you've got a hose and you put your thumb over the end of the hose. The fluid is still flowing out at approximately the same current, the same rate of flow in terms of volume per second. But if you pinch it off to a narrower aperture, then it has to be traveling at a faster speed in terms of distance per second to get the same amount of volume flowing through per second. So generally, if the two locations in a pipe with flow in it are different areas, different cross-sectional areas, then the wider one will have a slower speed and the narrower one will have a faster speed. They have the same current in terms of volume per second, but they'll have different speeds in terms of distance per second, and therefore different kinetic energy densities. So in general, if the two locations are the same cross-sectional area, again, regardless of what happens in between, if the two locations have the same cross-sectional area, you could ignore the kinetic energy density term entirely. Or of course, if the fluid's not moving, you would also ignore that term, regardless of the area. And then the other terms, pump is pretty straightforward. If there's a pump between the two locations you're comparing, you would include that pump term. If there's not, you wouldn't. Even if there's a pump somewhere else in the system, if there's not a pump on the path you're considering, if there's no pump along that path, then you would leave out the pump term. And then I times R, if either one of those is 0, if you've got no flow, then of course you'd leave this term out. And also if the pipe has no resistance, then you leave this term out. Strictly speaking, that's impossible. Every pipe has some resistance. But for a pipe that's very wide or not very long or very smooth, we could assume that resistance is maybe small enough we can round it off to 0. But be careful about that. If you assume resistance is 0 and the whole equation falls apart, that probably means you do need to include the resistance term. But yeah, realistically, every pipe does have some resistance, but if the resistance is very small, we might round that off to 0. Any other questions on that Bernoulli equation so far? All right, well, try out these ideas on the examples on your FNT, and we can look at some more example problem next time, and I'll see you then. You're welcome.